Welcome dear students once again to my YouTube channel Knowledge Entertainment. And today we are going to start another chapter of, especially from plus one mathematics, you can say non-medical, you can say arts with mathematics. And the name of the chapter which we are going to start today is Principles of Mathematical Induction. We are going to start this chapter, and before starting the chapter I want to make one request to all of you. If you know any students, especially of class 10 plus 1, who is poor, who cannot afford to pay large high fee in coaching centers etc., and want to prepare for CBSE board examination or IIT or any other competition, then kindly share my videos to him so that he may prepare accordingly for his examinations. We have covered the chapters of sets, set theory, relations and functions. We have completed trigonometry, and now we are going to start the fourth chapter, that is Principles of Mathematical Induction. Slowly I will try to complete all the chapters of plus 1 mathematics, and then I will move on to the plus 2 mathematics, then BSc and then MSc. I try to cover all the mathematics on my YouTube channel. So before starting, it's my humble request to share my videos with those students who cannot afford to pay high fees in coaching centers. So we are going to start this chapter, that is Principles of Mathematical Induction. So first of all, let us understand what is principles of mathematics, and before that, what is a statement. Normally, a statement is a sentence which is either true or false. So statement is a sentence which is either true or false. And in mathematics, we use the term statement in this chapter, Principles of Mathematical Induction. We denote it by Pn, and it depends upon n, and n is here the natural number. So n belongs to the set of natural numbers. So this is Pn. Pn is a statement. A thing is that you can draw conclusions from two statements to form a 3/3 statement that is definitely true. So here we will use this factor to solve the questions of principles of mathematics. And what is basically principles of mathematics? There are so many principles of mathematics, not one. Basically, we will consider the primary principle of mathematical induction. We will not move on to the secondary or dual principle of mathematical induction, but I'll try to explain all these. So, primary principle of mathematical induction, what it says? It says if P1 is true, and Pn is true, implies Pn plus 1 is true, then Pn is true for all n belonging to the set of natural numbers. What it means? Look at carefully. Here P1 is true. So P1 is true. And Pn is true implies Pn plus 1 is true. That means this P1 is true will imply P2 is true. So P2 is also true. Now Pn is true implies Pn plus 1 is true, and P2 is true. So P2 is true will imply P3 is true. And this P3 is true will imply P4 is true, and so on, and so on. So what you will get? You will get P1 is true, P2 is true, P3 is true, P4 is true, and so on. That means Pn is true for all n. So it is the basic principle of mathematical induction, which more or less we are going to use in this chapter. Then there is dual principle of mathematical induction. Dual method. Dual method says that if P1 and P2 are both true, P1, P2 are true, and Pn minus 1, Pn are true, implies Pn plus 1 is true, then Pn is true for all n belonging to the set of natural numbers. So let us understand it also. Here P1 is given to be true, P2 is given to be true. Now look at the second statement. Pn minus 1 is true and Pn is true. That means Pn plus 1 is true. Now P1 is true and P2 is true. So here n is 2, that means P2 minus 1 and P2 are true. That means P2 plus 1, that means P3 is also true. So P3 is also true. Now take these two. P2 is true, P3 is true. Compare here. P2, P3, Pn minus 1, Pn. That means your n is 3 now. So P3 minus 1 is true, P3 is true. That means P3 plus 1, it means P4 is also true. So P4 is also true. Now P3 and P4, take these two and compare with these two. So P3 and P4 true, that means P4 minus 1 and P4 are true. That means P4 plus 1, it means P5 is also true, and so on. So what you are getting, P1, P2, P3, P4, P5 and so on are all true. That means Pn is true for all n belonging to the set of natural numbers. The third one, that is the advanced principle of mathematical induction. Rarely we will use it here. It is advanced principle of mathematical induction. It says that if P1 is true, and Pn is true for all n less than m, implies Pm is true, then Pn is true for all n belonging to the set of natural numbers. Here m is also a natural number. So let us understand what it says now. We are given that P1 is true. Okay, P1 is given to be true. Now take m to be equal to 2. So what the second statement will be, Pn is true for all n less than 2. And there is only one n less than 2 natural number, that is 1. And P1 is true, we know. Since P1 is true for all n less than 2, that means P2 is true. So it means your P2 is going to be true. Now take your m to be 3. So Pn is true for all n less than 3. And how many n less than 3 are there? These are 2, 1 and 2. And you know that P1 is true and P2 is true. So that means Pn is true for all n less than 3. And it implies P3 is true. So that means P3 is true. Now take m to be equal to 4. So Pn is true for all n less than 4. And n less than 4 means n is equal to 1, 2 or 3. That means P1 is true, P2 is true, P3 is true, and they are already given to be true. So Pn is true for all n less than 3, less than 4. That means P4 is also true. So P4 is true, and so on. You will get all Pn is true for every n belonging to the set of natural numbers, and this is the third form of principle of mathematical induction. We know This is, we know it as advanced principle of mathematical induction. And now we will move on to some questions based on the principles of mathematical induction. So let us consider some questions. The first question taken to be as prove that question is prove that n cube plus 2n, it is n cube plus 2n is divisible by 3 for every n belonging to a set of natural numbers. Now, where there is a question involving a statement, this is your statement that n cube plus 2n is divisible by 3. This is your Pn. This is your Pn, the required statement. And we are to show that Pn is true for all n belonging to the set of natural numbers. And wherever there is a problem in which we are to prove that Pn is true for all n belonging to the set of natural numbers, the best way is to use the principles of mathematical induction. So we will start with P1. The first step, P1. P1 is 1 cube plus 2 into 1 is divisible by 3. And this is 1 plus 2, that means 3. So 3 is divisible by 2 is true. And which is true? Which is true. That means P1 is true. So P1 is true. The first step is okay. The second step we will assume. So let P n be true. The second step we are to assume that Pn is true, and the third step we will prove that Pn plus 1 is also true, because what we need, Pn is true implies Pn plus 1 is true. That is the main step. So we have taken Pn to be true, and we will prove that Pn plus 1 is also true. Now Pn is true. What is meaning of this statement? Pn is true. So Pn is true means n cube plus 2n is divisible by 3. If a quantity is divisible by 3, then definitely it is a multiple of 3. So it can be written as 3 into some natural number. So therefore there exists some natural number p belonging to the set of natural numbers n, such that this n cube plus 2n is equal to 3p, because n cube plus 2n is divisible by 3, so it is a multiple of 3, so it can be written as 3p. Now we will move on to the third step. Third step means Pn plus 1 is true. So what is your Pn plus 1? Pn plus 1. For Pn plus 1 you will have to put n plus 1 in place of n in the given statement. So what you will get from here is n plus 1 cube plus 2 times n plus 1. Open the bracket carefully. You will get n cube plus 3n square plus 3n plus 1 plus 2n plus 1. Now you are given that n cube plus 2n is equal to 3p. Here you are having n cube plus 2n. So this is now equal to 3p because of our assumption. So it is equal to 3p plus this is your 3n square plus this is your 3n plus this 1 plus 2 into 1, here it is 2. So this 1 plus 2 is equal to 3. And now you can take 3 common from it. So it is 3 times p plus n square plus n plus 1. Now if a quantity is 3 times something, that means it is a multiple of 3, or you can say it is divisible by 3. So that means your n plus 1 cube plus 2n plus 1 is divisible by 3, because it is coming out to be a multiple of 3. So this means n plus 1 cube plus 2 times n plus 1 is divisible divisible by 3. And what it is now? Look at this statement and compare it with this. This is your Pn. So what it is? It is your Pn plus 1. So this means Pn plus 1 is true. Now, look at what we have proved. First, we proved that P1 is true. Then we assumed that Pn is true, and we have proved that Pn plus 1 is true. Therefore, by principles of mathematical induction, by principle of mathematical induction, in the coming times we will write it as short as PMI. PMI means principle of mathematical induction. So therefore, by principle of mathematical induction, Pn is true for all n belonging to the set of natural numbers, which is our required result. So this was the first question which we have proved using the principles of mathematical induction. And now I'll move on to the second question. So let us take another question of principles of mathematical induction. The question is, show that. The next question is, show that 1 plus 2 plus 3 plus 4 plus and so on up to n is equal to n into n plus 1 over 2. This we are to prove, and this we are to prove for every n belonging to n. So it is your statement. Now, your statement is this. This is your Pn. And we are to show that Pn is true for every n belonging to the set of natural numbers. Therefore, we can use the principles of mathematical induction. So first, let us have a look on P1. What is your P1? In P1, what the left hand side of the statement will be? It is starting from 1, then summing up, and the last term is n. So it is in Pn. In Pn the last term is n. In P1 the last term will be 1. And what is the first term? It is also 1. So what will get? Only 1 on the left hand side, and on the right hand side, putting n is equal to 1, I am going to get 1 plus 1 divided by 2, which is also 1. So 1 is equal to 1 is true. So this means P1 is true. P1 is true. So the first step is completed. P1 is true. Now what we have to do? We have to assume that Pn is true. Assume that Pn is true. And Pn is true means this statement is true for n. So that means 1 plus 2 plus 3 plus and so on plus n is equal to n into n plus 1 by 2 is true for n. Now we have assumed the statement to be true for Pn. What we have to prove? We have to prove that the statement is also true for n plus 1. That means Pn plus 1 is true. So let us move on to Pn plus 1. Pn plus 1. What your left hand side will be? In Pn, you started with 1 and added consecutive natural numbers 1 plus 2 plus 3 plus 4, and the last term was n. When you will be considering Pn plus 1, the last term will become n plus 1. So left hand side will be 1 plus 2 plus 3 plus and so on. At the end you will get n plus 1. Since the difference of the terms is 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1, and so on. So before n plus 1, the second last term will be n. Because after n you will get n plus 1. After 2 you are getting 2 plus 1. After 3 you are getting 3 plus 1. After n you will get n plus 1. So it is further equal to. Now in your assumption you have supposed that this is equal to n into n plus 1. So substitute the value here. It is n into n plus 1 by 2, and plus there is one more term, that is n plus 1. Now this is your one term, this is your another term, and in both these terms there is n plus 1, so n plus 1 can be taken out. So I am taking n plus 1 out. What I am going to get is n by 2 plus 1. And this is now n plus 1, and by taking LCM 2 here we will get n plus 2 upon 2. This is your left hand side of Pn plus 1. And what is your right hand side? Right hand side of Pn plus 1. So put n plus 1 for n here. So this n will change to n plus 1. And within the bracket this n will also change. So you will get n plus 1 and plus 1. So that means n plus 2 over 2. What is your left hand side of Pn plus 1 is n plus 1 and plus 2 by 2. And what is right hand side of your Pn plus 1 is again n plus 1 and plus 2 by 2, and they are equal. That means Pn plus 1 is true. So we can say now Pn plus 1 is also true. Once again, what we have done, P1 is true, we have proved, we have assumed that Pn plus 1 is true, and we have proved that Pn plus 1 is also true. Therefore, by principles of mathematical induction, PMI, we have this Pn is true for all n. That means 1 plus 2 plus 3 plus and so on plus n is equal to n into n plus 1 by 2 for all n belonging to the set of natural numbers. So this is another question which we have proved using the principles of mathematical induction. And now I'll prove more questions on principles of mathematical induction to make it an easy concept for you, so that you may be easy to deal with the principles of mathematical induction. Another question I am going to take is prove that. The third question of today I am going to take as prove that 1 into 2 plus 2 into 3 plus 3 into 4 plus and so on plus n into n plus 1 is equal to n plus 1 n plus 1 n plus 2 upon 3. Let me verify the statement. If it is true, yes, okay, it is right. So we have to prove this for every n belonging to the set of natural numbers. So here I am not going to mark which is Pn. Now you know that what is your Pn. This is the left hand side of your Pn. This is the right hand side of your Pn. And once again we will proceed as we have completed in the previous question. So for the solution, what is the first step? Now I think you know it better. First we have to prove that P1 is true. So what is P1? P1. In the Pn, this is your Pn. In the Pn, you start with 1 into 2, then plus 2 into 3, then plus 3 into 4, and so on. The last term is, because it is Pn, the last term is n into n plus 1. In P1, the last term will be 1 into 1 plus 1, that means 1 into 2, and it happens to be the first term also. So what you will get in P1, you will get 1 into 2, that means 2 only. On the left hand side, this is your left hand side of P1. And what is your right hand side is substitute n is equal to 1 here. So you will get 1, 1 plus 1, 1 plus 2 divided by 3, which also happens to be equal to 2. So left hand side is equal to right hand side. That means P1 is true. So first step, the first hurdle we have cleared. Now the second step we have to assume. So suppose that Pn is true. So Pn is true means 1 into 2 plus 2 into 3 plus 3 into 4 plus and so on n into n plus 1 is equal to n plus 1, n plus 2 upon 3. This is true, as we have supposed that Pn is true, and now we will show that Pn plus 1 is also true. So let us first look at left hand side of your Pn plus 1. What is your left hand side? Again, you will start with 1 into 2 plus 2 into 3 plus 3 into 4 plus and so on. What will be the last term? In Pn, the last term is n into n plus 1. In Pn plus 1, the last term will be n plus 1, n plus 1 plus 1, that means n plus 2. So the last term is going to be n plus 1, n plus 2. And just give a look on this statement, and it is very much clear that the second last term will be n into n plus 1. So it is equal to. Now this term, you see, because of the assumption that Pn is true, this happens to be equal to n plus 1, n plus 2 by 3. So substitute the value here. You will get n plus 1, n plus 2 by 3, and plus there is one more term, that is n plus 1, n plus 2. Now you are having the sum of two terms, and n plus 1 is in the first term and is also in the second term, n plus 2 is in the first term and is also there in the second term. So n plus 1, n plus 2 can be taken out as common. So n plus 1, n plus 2 I am taking as common, and what the rest term I am going to get is n upon 3 plus 1. And just take out the LCM from the third term, rewrite it, you will get n plus 1, n plus 2, n plus 3 upon 3. And now look at right hand side of your Pn plus 1. Right hand side of Pn is n into n plus 1 into n plus 2 by 3. So what will be the right hand side of Pn plus 1? It will be n plus 1, n plus 1 plus 1, that means n plus 2, n plus 1 plus 2, that means n plus 3 by 3. So the right hand side is n plus 1, n plus 2, n plus 3 over 3, which happens to be equal to the left hand side of Pn plus 1. So Pn plus 1 is also coming out to be true. So what you are going to get from all this calculation? From all this calculation, you obtain that Pn plus 1 is true. Pn plus 1 is true. You prove that Pn1 is true. You suppose that Pn is true, and you proved that Pn plus 1 is also true. Therefore, by principles of mathematical induction, what you prove that Pn is true for all n belonging to the set of natural numbers. So this is the proof of this question, and I'm going to take one more question today, and then we will take some typical, some difficult, some more difficult, and you can say tricky questions in the next video, and maybe in next to next video also, because principles of mathematical induction is a very important topic from the point of view of various examinations. So we will solve various type of problems in the coming 2, 3 or maybe 4 videos. So what the next question I'm going to take today is, this is a very interesting question. So question is prove that 1 plus x square plus and so on plus x raised to the power n is equal to x raised to the power n plus 1 minus 1 upon x minus 1 for every n belonging to the set of natural numbers. This is the statement of the question. So this is your Pn. Now, in the solution, as in the previous questions we have seen, what we are to prove, first we have to show that P1 is true. So what is left hand side of your P1? So we are talking about P1. What is the left hand side? In Pn, this is your Pn, this is your Pn, this statement is Pn. In Pn, you are starting with 1 and the last term is x raised to the power n. In P1, the last term will be x raised to the power 1. That means x. So x will be the second and the last term. So the left hand side will become 1 plus x. What will be your right hand side now? Right hand side, substitute the value of n to be equal to 1. You will get x raised to the power 1 plus 1 minus 1 upon x minus 1. That means x square minus 1 upon x minus 1. And the factors of the numerator are x minus 1, x plus 1 divided by x minus 1. X minus 1 will be cancelled out and you will get 1 plus x, which happens to be equal to your left hand side of P1. So it means you have proved that P1 is true. So first step, that means first hurdle is being overtaken. We have proved the first step, and the second step, we will assume that Pn is true. Assume that Pn is true. And Pn is true means this 1 plus x square plus and so on plus xn is equal to xn plus 1 minus 1 upon x plus x minus 1. This is your Pn, and this we have assumed that is true. Now we move on to Pn plus 1. So what is the left hand side of Pn plus 1? Pn plus 1, left hand side. In the left hand side of Pn, the last term was x power n, and in Pn plus 1, the last term will become xn plus 1, and xn will be the second last term. So left hand side of Pn plus 1 will be 1 plus x square plus and so on x power n, and one more term xn plus 1. Now this sum 1 plus x square plus up to and so on x power n, as per our assumption that Pn is true, this is equal to xn plus 1 minus 1 upon x minus 1. So I am going to substitute the value here. It will become x n plus 1 minus 1 upon x minus 1, and plus there is one more term x n plus 1. Now take out the LCM of these two terms. Taking LCM as x minus 1, this numerator will be as it is xn plus 1 minus 1, and here xn plus 1 will be get multiplied by x minus 1. Multiplying, you will get two terms. The first term will be x n plus 1 into x, that means x raised to the power n plus 2, and the second term will be xn plus 1 minus 1 is minus xn plus 1. This xn plus 1 and minus xn plus 1 will be cancelled out, and you will be left with x n plus 2 minus 1 upon x minus 1, which is nothing but the right hand side of your Pn plus 1. So this is right hand side of your Pn plus 1. By putting n plus 1 in place of n, you will get x n plus 1 plus 1, that means xn plus 2 minus 1 upon x minus 1. So this means Pn plus 1 is also true. You prove that P1 is true, then you prove that you assume that Pn is true, and you prove that Pn plus 1 is also true. Therefore, by principles of mathematical induction, Pn is true for all n. That means the given statement is true for all n belonging to the set of natural numbers. So I am going to stop this video here, and I would like to request you once more to kindly share my videos with needy students of 10 plus 1 who have taken mathematics as an optional subject, so that they can be helped out. So once again, I'd like to thank you for liking my videos, for sharing my videos with needy students and subscribing my channel. Thank you once again.